Alright, so hello everyone. My name is Bhavesh Dhake. Now, today, first of all, I would like to let you all know that whatever content will be taught in this video is not mine. I have learned it from this book, Windows Security Internals, written by James Forshaw. Now, from this book, the first chapter is the basics of PowerShell, which we will be skipping right now. I will be teaching about the second chapter, which is the Windows kernel. This chapter is all about its components and their functionalities, and a view from how we can see them practically via the PowerShell. Now, there are two types of notes that I have created from this book. The first one is where I have copy pasted from the book all the important points and screenshots of the practicals from PowerShell. And second are my handwritten, which are the logic flow diagrams, which is in short. So I will be mostly teaching from my handwritten notes, and for the practical part, we will be watching from this PDF. So, starting the chapter kernel. Now, first of all, kernel is can be defined as the heart of the operating system. Basically, on our hardware, we believe that we use directly the operating system. However, the operating system that we use is the user level application. The major and core component is called the kernel. Now, this is a diagram of how the kernel works. Let me minimize it. So, here we are. We are on the user application. Now, after the user application, which is in user mode, there comes the kernel mode, the system, which comprises of all these several components, which all work together and in the flow. We can see that how the request from user application goes to the system call interface, from there to the memory manager, code integrity, and other path is the security reference monitor, object manager, and etc. all components. Now, first of all, we will take a overview of how these components work and what functionality do they give, and then we will dive deep into it as per the book of flow. So, overview, the user application, its examples are basically our user applications like the Chrome, MS Word, and any kind of app or etc. software that we can use on your main OS. Now, the problem is the user applications cannot directly access the kernel functions. Second is the system call interface. Basically, the gateway which allows us users and user application to access the kernel functions is called the system call interface. Third one is memory manager. It is self-explanatory. It manages and controls different types of memory. Fourth one is code integrity. The main function of code integrity is to prevent unauthorized code execution, which means that there can be different types of code on your system which can be authorized by the system or malicious. Security reference monitor. It is basically the central manager of the security access. Object manager, it does the resource management. Configuration manager, it manages the database system configuration. Not the database of the web development, the database of our OS, meaning the different types of files that exist in your operating system and their configuration. Input output manager. Now here too, input output does not rely only on the physical hardware that we usually know. We will dive deep later in the course. Process and thread manager. Basically, the any kind of program or task that goes on your system computes in form of process and its threads. Advanced local procedure call. It is used for the communication of all these processes that goes on in the system. And drivers are basically the interfaces for the hardware and software devices that we use. Now, all these different kind of components that we saw in this diagram, they all are communicating. I have represented them using the arrow, and all these arrows are called APIs. From technology, you all will be knowing application programming interface. They are different kind of here. Okay, so when we talk about these APIs, all APIs have different names, and according to the subsystem they are used for, they have different prefix into their name. We have given a table here. The main that we will be focusing here is the system call interface, which is its prefix is NT or JW. You can read all others. Now we will start with the component, the security reference monitor. Now basically this is the security mechanism which restricts, like basically, like we know the authentication and authorization mechanism that we usually see in network protocols, etc. It is the same kind of here, just for the operating system, which describes that which user has access to what kind of resources. We can see from a diagram here, we are the user process here. We want to access this resource. So our process will go to the kernel, to the security reference monitor. It will communicate with the resource and it will check. And if we have the access, our identity account, then it will grant us the access or it can deny us. Now in the system, every process that is generated, like every task which creates a process, has an access token into it. This access token is managed by this security reference monitor, and this access token has details in it. Which kind of details? It defines the identity of user from which this process was created. And basically, when we talk here, the SRM communicates with the resource that whether we have to give your access to this user or not. Here he was checking with the security descriptor of the resource. Basically, it is the component of resource which holds the data, that what kind of users it has access to and which should be denied. So basically the access token was compared with the security decryptor's access check, and from there we got to know that does the user have access and to what level. Also the function of SRM is to create audit events, which means that which user accessed which resource, kind of logs. Now the security reference monitor, it considers users and groups not in the form of name but in the form of binary structures, which are called security identifiers, SIDs. Now, from the problem is we users can read our name, but we cannot read our SIDs, a form of binary structure. But SRM on the other hand is reverse. It can read the SIDs but not the name. So we, in order to work for the users to SRM, we have to make a conversion of name to SID. Therefore, here comes into the play Local Security Authority Subsystem, LSASS. Basically, this system does the name to SID conversion for users to SRM, and this system, of course, it can be misused in malicious ways. Therefore, it is user independent. Like this, LSAS works directly on the kernel mode, and it is independent from any logged in user, even admin itself. So the security, okay, and the SID which is generated, it is generated in a string format. And to convert this binary structure into string, this work is done by the security descriptor definition language, abbreviation SDDL. So remember the two things, LSAS, the subsystem which converts name to SID, and the SID is converted into string format by SDDL. Now SDDL along with the SID also has the responsibility of entire security descriptor, which may have various other details about the security of the resource. In PowerShell, we can do this via this command. Let's go to this PDF. Okay, so here is the command, get hyphen nt sid hyphen name double quotes users. Now we will look into it. Get means basically to fetch some data. The nt, as we discussed earlier, it is the system call interface prefix, and sid, what we discussed right now, the security ID. Now we are asking the system to get the SID of the system call of only those components we are supplying here the parameter hyphen name whose group is users. So here in output we got the domain built in with path users and it says SID. Now this SID is having various components with hyphens. We will discuss about it. Now see the difference here. When we use the parameter name users, it responded with the SID of only users, which was in built-in domain. But when we removed the parameter used only get NTSID, it got us the SID of our main system. For my case, it was my desktop, my device name, and my username. and this was my SID. Let's discuss about the SID. So basically, in okay, the SID, the S stands for the HDDL SID. Like this tells us that the following part is our SID. Now the one number which was here, it means the version. The 5 number, it means that what kind of security authority do we have. And 32/45 which we had in both the outputs here. Uh, so basically it means that it describes the NT authority group. Now of course I am the user and I am myself the admin. So I have the system call interface. So I was in the NT authority group. Now to revise what the security reference monitor did, we are a user. The user wants to do some task, so it created a process. This process has access token. This access token is analyzed by the SRM. SRM, after taking an access check, it gives the SID, which is worked upon by the HDDL, which converts the name to SID. And this, after the access check, either we get the grant to the access or we get denied. The next component is the object manager. Now, in Windows, when we talk about kernel, everything in the kernel, whether it be a file, a process, a thread, or anything, it is stored in the form of object structure. Now, every object has a security descriptor, which of course, like the last one tells that which user has which kind of access. Now, there are different types of access that a kernel object can have, like read, write, and execute, and all. Now, this kernel has an object manager, and this object manager manages the kernel objects allocation, lifetime, resources, etc. things. So, like basically everything that we have in the kernel, the memory, is present in the form of objects, and these objects are managed by object manager. And every object in the kernel has a unique functionality. Now, when we put this command in PowerShell, let's go to the slide. When we put this command get entity type, entity means the system call, type means types of the objects, then we can get a long list of whatever types of objects are present. Now, like in user, like in our OS, we have this file manager, the file system which stores data in form of files, different extensions and different types. But in kernel, the file system which stores the kernel objects is different, and it is called Object Manager Namespace, OMNS. Remember this abbreviation? Object Manager Namespace is abbreviated as OMNS. We will be using short form further. So basically, this OMNS has directory objects in it, not directory objects. And inside this directory objects, we have our kernel objects. And each of these directory objects has a security descriptor. So like earlier we said, every object has a security descriptor, as well as the directory object in which it is present also has a security descriptor. Let's go to the further slide of the PowerShell. When we put this command, which is stated here, ls NTObject --/ pipe sort object name. Basically, this command tells us that list all the types of objects on the root path and sort them by object name, like by their name. As we can see in this output, we have the name and we have type name. So there are various objects and their types. Some are directory, some are filter connection, job, etc. etc. Now, here if you see the last one, I will zoom. There's something called symbolic link. Now let's discuss what is this. Basically, the functionality of symbolic links is to redirect one path from OMNS to another. Let's look this whole object manager thing through a diagram. This is our whole kernel. Inside kernel, we have our object manager. Inside the object manager, we have our object manager namespace. And this object manager namespace is what handles our all kernel objects. As you can see, both the namespace and the kernel objects have their own security descriptors. Next component is the system calls. Now, like I told you, that user mode applications cannot directly access the kernel function. So the gateway that enables this is called system call. Now, a short diagram that we can see that a user mode app creates a process. This process creates a system call. Now, this system call goes to the kernel on behalf of the user. From this kernel, the request goes to object manager, from object manager to OMNS, and from that to kernel object. Like the user requested the access to this object, so it had to went through all these components to reach here because it cannot directly access the kernel. Now, basically, the system call, as we discussed earlier, its name starts with the prefix NT or ZW. Now, in system call, there are various verbs. These verbs define that how do they operate on a specific kernel object. Now, there are four types of verbs here. First one is creating a new object. Second one is open an existing object. Third one is querying the information and properties of an existing object. And fourth one is setting the information and properties new to an existing object. Now, again, we will see a diagram here. The diagram shows that from user, it creates a process. I will maximize. From user, it creates a process. The process has multiple threads. And from thread, it goes to system call to mutant object, and then are remaining as usual path: kernel, object manager, OMNS, and kernel object. Now, you must be wondering what are these two new things, thread and mutant object. So let's discuss. Basically, when a task is created, it has a process creation after it, and each of this process can have one or multiple threads. Like this thread is the component that accesses the kernel object. Now, there can be a case where a process has multiple threads from it, and all those threads are trying to access one specific kernel object. But as you might know, the concept of deadlock, where multiple threads try to access an resource, and it creates a keep on waiting situation, and that's why the system keeps waiting and crashes. So here comes into to play mutant object. Now, basically, what mutant object does is, even if the process creates multiple threads and all these threads are going to the system call, the system call creates a mutant object. Now, the main functionality of this mutant object is, even if it is given thread 1 and 2, for example, scenario, it will consider only one thread out of them both and supply that one thread ahead to the kernel. This will prevent deadlock. So we can create a mutant object ourselves using this NT-create mutant syscall. Now the structure of NT-create mutant syscall is shown here. Of course, we can see that these are all the data types and these are the names of the structure. We will discuss them one by one. So basically, what is NT status? Basically, this is our function NT-create mutant, and the type of data that it will be returning is NT status type data. Second is handle asterisk. Of course, I am expecting all of you guys to have basic programming knowledge before watching this video. So you must be knowing that asterisk represents a pointer, usually in our C language. So basically, handle means a pointer which refers to a kernel object, which means that we are not directly accessing to a kernel object. Instead, we have a address of a pointer, and that pointer has the actual kernel object address. This is for security reason, of course. So here we are giving a outer bound pointer. Second is access mask. Now access mask is basically the level of access that we have. Then we have object attributes. Of course, it is in the name it is given the attributes of the object. And last one is boolean. Now boolean initial owner. It basically means it can hold only two values, true or false, which means that we have been granted or denied the ownership. Now here we are talking about the attributes. These are all the possible attributes that a object can have. First one is, can it be inherited by a child process? It's the Object permanent, can it be destructed? Exclusive, does it has access to only and only one process? Case insensitive, can it be can it be operated on by using any kind of uppercase and lowercase in its name? This one is basically, if the object is already existing, then directly open it, give it a handle to that object. This one says that if the object is linked to any other object, like using symbolic link, then open it. This one says that when the object is in kernel mode, give us the kernel handle. This one says that force access check. Like basically, even if the thing isn't suspicious, we have to compulsory do an access check that does the user necessarily have access to this object and what level of object access. Last one is ignore impersonated device map. So if it suspicious that the device is mapped, like not the original one, then we'll ignore the access. And last one is don't reverse. Like basically, if you found a symbolic link in the way, do not follow it. Then end status that we saw, the main type of the function. What is it? End status code. Basically, all the system calls return us with an end status code. Like for example, success, like the access was success, access was denied, any error, etc. Now this code is of 32-bit. It has this 5 components. The first 15 bytes are the status code. From 16 to 27 bits, it's the facility. The 28 is the reserved bit. The 29th is the customer code, and 30 to 21 is the severity bits. Now severity bits have these 4 types. If the access was a success, it will have the value 0. If the return was informational, it was value will be 1. If a warning was written, it will have the value 2, and if an error was encountered, then it will return the value 3. The customer code, basically it tells us that this object was Microsoft defined, like it was the own systems, or it was defined by, this code was defined by any other third party. If it is by Microsoft original, then it will return the value 0, and if it was not by Microsoft but someone else, then it will return value 1. Now result bit is always having the value 0. Now facility means the component or the subsystem to which the object belongs. Now here the default value is 0. If it's from debugger component, then its value will be 1. And if it is from the Win32 API, the Windows 32-bit APIs, then the value will be 7. Now status code. Now this status code, this is unique for each facility. Like for every facility that we have, for every component, this will be unique. And it is decided by the implementer, the own system. And okay, so to get the status codes, we can use this command in the PowerShell. So here if you put the command get end status, it will return us with all types of status that we have for every kind of existing status and the message that it gives us. For example, the status was success, it is waiting for resources, and other kinds of. The next one is object handles. Now basically, when we talked about the procedure where the user process is sent to the system call, and from system call to the kernel to object manager to the namespace to kernel object. Now there's one more component in here. Basically, uh, the object manager has a pointer to the kernel memory. Let me explain it. Basically, the system call, when it, like the initial part was done, like the access was given to the kernel, and it has been checking that whether the user is to be granted access or not. Now, in case the user is granted access, a kind of handle is returned to the user. Basically, after the work is done, system call gets an response from kernel. It returns the handle to the process that was created by the user for the specific task. And this process uses this handle to again access the actual kernel object. Now, this handle table has 3 components. If you guys are kind of confused at what is this handle and all, It will get clear as we further go into this topic. The handle table has three components. First one is the numeric identifier of the handle. Second one is the level of access that the handle has. And third one is the actual pointer to the kernel memory, to the kernel object that we requested to. This will be used to access the kernel object. This will be the R verification that we can access this object, and this will be the identifier, the ID of our handle. Now let us see this diagram. From there it will be totally clear. Basically we are a user. The user creates a task. The task has a process. This process sent the request to access this kernel object in form of a handle. This handle was applied to the system call. This system call then sent this handle to the kernel API. This kernel API then checks that what type of access is the user requesting and what type of kernel object is the request given by the user. Then if the user account and ID is allowed this type of access and this type of object, then the request will be approved. Then the things will go to a handle table. In this table, the handle that was given by the user will be converted to a kernel pointer, and this pointer will be returned to the user in form of a handle. So basically, this is our handle which was initially sent, which does not has the access to this kernel object. This handle was inspected by the kernel API. It checked that whether this user should be given the access. It can have an access. So basically, a pointer to the kernel object was created, and this pointer was based in the handle. And this handle consisting of pointer was returned to the user. Now you will be wondering that this part, which did the, of course, from security perspective, this is the main part, that the kernel API did a check on the type of access and what kind of object type was the user requesting. Now, how did the kernel API check this? So here we introduce us to the new concept, which is access mask. Basically, this is the concept which was used here, which told the kernel API that whether should we approve the request or should we deny. Now, access mask. Basically, it is in handle table, and access mask tells that what kind of the access should be granted or not, and if it is to be granted, then what level of access is to be granted. Now, the access mask has four components. The first 15 bits are the type specific access, 16 to 20 are the standard access, 21 to 27 are the special access, and 20 to 31 are the generic access. Now here, the type specific access, it basically defines that what operations are allowed to the users to do on the kernel object. The standard access, it tells us that what operations are allowed on any kind of object of kernel. Can you see the difference? Type specific, like its name, for only a specific type of kernel object, what operations are allowed. And standard access, for all kind of objects that we have access to, what operations are allowed in general. Now, what are the types of operations that can be done? First one is delete the object. Second one is read the security descriptor of the object. Security descriptor, if you remember, it is the component of the resource which has all the information about the security allocation, etc. of the resource that should it be authenticated and authorized to the specific user. Then write the security descriptor new values. Then write the owner of the security descriptor of the object. And last one is synchronize, that should it wait for any other process, etc., or should it continue. Now the third component, special access. Now special access, basically it defines the access of two components. First one is access system security, which tells us that can we read and write the audit info. And second one is max allowed access, that what all maximum we can do using the handle. And generic access is basically the whole thing, the request that we give to the system call to the kernel API. So like you must be wondering that in this process, when we sent initially the handle to the system call. It must be empty? No. The handle value had this generic access value field, which told the system API what kind of request are we doing for the kernel object. Now, basically, this handle was converted to kernel pointer or kind of has the kernel pointer, and this conversion is done by the generic mapping table. Now the generic mapping table defines what all different kinds of access do we have to a kernel object, like read, write, execute, or all. These are represented by the R, W, E, and A. You can see them in this PDF. Okay, here you can see the pictorial depiction of the thing we were talking about. The user process, it sends handle. It was given to the system call interface, and it was all analyzed by the kernel API and converted to pointer in the handle table. And there goes our mutant object and mutant type. Here, if we give the command get entity type, type of the objects, and select by name and generic mapping, then we can see R, W, E, and A, read, write, execute, and all, and what kind of mapping do we have to each of the type. Now, you all must be very confused that what all concepts we saw, how are they logically connecting to each other. Don't worry, I have made a diagram for this. Now let's go from the starting. First of all, we are a user one. Suppose we want to do some task. So we generated a process. This process had a thread, and this thread, which was in form of a handle, was supplied to the system call. From system call, the handle was supplied, converted into a mutant object, of course, because if the process had multiple thread 1, thread 2, then the mutant object is necessary to forward only one thread. Now here we have the thread from handle. Now this was put further to the handle table, just we saw in the picture in the other video. Now in this handle table is where all the process is being done. In the handle table, the kernel API now analyzes the requested handle by the process, the user. Now first of all, it checks the access token of the handle, and it compares it with the security descriptor of the resource from the access mask. Access mask is what defines that what kind of access and what object type can the user access. Now after analyzing the access mask, it can either deny the grant of kernel object or it can approve. Now in case the request is approved by of the user, the handle is then converted to the kernel pointer, and this kernel pointer is what put in the handle and given back to the user. Of course, not directly given, the handle is along given to the system call, and then it is given back to the process. And this kernel pointer, the handle was converted to what? The kernel pointer. And this pointer is what pointing towards the kernel object. This is the thing that we requested in the process. And this kernel object is what consists of the kernel memory, the actual data that we wanted. So this is the whole diagram. I will be sharing both of these PDFs in my GitHub, and the links will be given in the description. You all can access all these handwritten and elaborate notes, and I would request all of you to read all of these notes by yourself. These are barely 70 pages, few hours of work, and you will get it more perfectly. This is my first time video, so I may not be that much explanatory. Now let's move to our new concept. Now this is an interesting concept, handle duplication. Now try to understand the process that we created has one handle. This handle has a specific type of privilege like read or write or execute to a kernel object. Process has the handle with this privilege. It can do this operation to the kernel object. Okay. Now basically, if this handle one is destroyed, like this kernel object has only one handle to a process, and if this handle is destroyed, then the kernel object will be destroyed automatically. So here, what malicious things can be done is basically the process has handle one privileges to the kernel object. Now what we will do here is we will create a new handle, a duplicate handle from this handle 1, which will be handle 2. This handle 2 will be given another set of privilege y. This privilege y can be less or more than the privilege x, like it can write or execute. And this handle 2, we will set a different kind of policy on it. For example, anti-destruct policy. After we set the anti-destruct, anti-close policy on the handle 2, now for example, this handle 1 we were created in this first case. The process had a handle 1, it had a specific privilege to the kernel object. Now suppose in case we forgot to close this handle. In case of that, a specific component called garbage collector of the system, it automatically closes the handle and destructs the object. But after we set an anti-destruct policy to the handle 2, what happens is even the garbage collector himself, the system, cannot destruct this handle 2. So it means the handle 2 will always remain alive and connected. And this handle 2, as it is mapped and duplicate of handle 1, it will have the privilege y access to the kernel object, which means that even if the handle 1 is closed by the user himself or by a system garbage collector, we will always have a handle 2 access to the kernel object. And as this handle cannot be destroyed, the kernel object cannot be destroyed. So we will always have this object alive and privilege y handle to the object, to this user. We can see here process handle when destructed. So here the access is gone, but the kernel object is still as it is. Why? Because we have a privilege handle 2 by the process which system can't destruct. Now moving ahead, wait, we can see this from the PowerShell. Okay, so I guess this is, yes, the handle duplication. Now if you can see this, basically what we did here is $mut. This is the mutant object that we created using the NT-mutant API call from this directory. Then from this command we checked that what all access does this mutant object has. It has a modify state, delete, read, control, write, write owner, and synchronize. All types of access this mutant object has. Now what we did is we created a duplicate mutant object. We created a duplicate and imported it from the original mutant object. So right now, when we compare the mutant and duplicate object, they both have the same kind of privileges, as you can see here. But now what we do is, since a mutant object, a handle, what access it has, a privilege to a kernel object, it is decided by the access mask. So what we did here is we created a mask object, an access mask from the NT access mask, and gave it the privilege of modify state. And then we simply implemented this mask on the duplicate object. So now the duplicate object has a privilege of modify state only. So you can see what was done here. We have a mutant object, original. We created a duplicate, DOP. It initially had the same privileges like the mutant object. But later on, we created a separate access mask. We implemented it on the DOP, and now the duplicate object has only modified it instead of all of these privileges. So here we created a duplicate object which has less privileges than the original one. And later on, we can see here, if we give the mutant object protect from close is equal to true, which means that after this application of this policy, even if we try to close this object, it cannot be closed even by the system itself. So this means that we have an object to a specific kernel object and we have a specific privilege to it, and it cannot be closed by the system. So the kernel object will always be there. So moving on. Now, what are the query and set information system calls? Now, basically, when we talk about a kernel object, it has information stored about its state. Now, when we talk about this state, the structure that is used to define all this, there are 5 parameters given about the state. First one is the object handle, like the actual handle which is given to the kernel object to a user. Second parameter is the type of process information, like what kind of process is it to which we have given the handle. Third parameter is the enumeration of names of information classes, like all types of information classes that are there. Fourth parameter is the buffer length to receive the info. For example, if we are to receive a specific kind of information from a process, then we need to receive it and store it in a memory location. But we have to give and allocate a specific amount of space in which we can sufficiently store that info, which is called buffer data. And fifth parameter tells us that if the retrieving was success, then out of this allocated buffer data, how much data was actually used. Moving next, we have the input output manager. Now, like I told you earlier, here the input output manager does not only mean about the physical hardware input output that we usually think of, like mouse, keyboard, etc. Now, here, the first statement which says is basically the work of input output manager is to define the access to the input and output devices via device drivers. Basically, the interface through which we can communicate to these devices with our system are called drivers. Now, the input output manager, which is also called directory, has two types of usages. First one is the physical device drivers, like your mouse and keyboard, that we all know. But second one is the file system drivers, the file system that we are using here right now, the user mode and the kernel mode. Even that file system access input output is managed by a driver in the input output manager directory. Now, for example, if we want to load a new driver, we can use this specific system called NT-load driver. Now, let's talk about the directory or the input output manager that we are talking about here. Now, if we are to enumerate the list of the contents that this directory has, we can only do that as an admin, not at all as a normal user. However, we don't actually have a need to enumerate the list of directory for our normal task as a normal user. However, we can interact with the drivers, our devices of input output, via a specific device object. Now, basically, when we talk about the directory, the input output manager, it creates specific drivers. And these drivers use this specific API from the system to create device objects. Like, for example, if you have a mouse, then the mouse, or for example, a file, it will have a specific object. And these objects are created by the drivers, which are created by the directory. And for example, if we have a kind of driver which does not have requirement of any interaction from the user, then in that case, it can have even zero device objects. Now, for a user to interact with the input output manager, there are no direct system call like the earlier system call that we discussed in the course. However, via the usage of file objects, we can interact with the device. Like, are you understanding? Like, to interact with a device which is managed by the input output manager, we cannot directly call the input output manager by the system calls. However, we can use file object system calls, the different types of system calls. Now, basically, what it says is our physical system, like our hard drive, uh, upon which the operating system, etc., things are kept, like the main medium, which has our both OS and our keyboard, mouse, etc., drive devices. Now, this hard drive has a location called system root, which is a part of the object manager namespace. Like we discussed earlier, in the kernel, there is object manager, and object manager has a object manager namespace, which has all the kernel objects. Now, the significance of this system root is it acts like a symbolic link, like it redirects a system to the Windows directory. So, what we here are trying to say is, basically, if we implement system root into the system drive, then it can not only help us interact with the hardware devices like mouse and key, but also help us interact with the actual Windows directory, our files manager and kernel, etc. Now, the type of files that in this Windows directory can be of different types. Like the most common example is our executable files. For example, our notepad has the file called notepad.exe. So this is a portable executable file in the Windows directory, which you can access via the symbolic link of system root. Let's understand this via a final diagram. You are a user. We search for the system root, which is a symbolic link. Like we are searching for a disk, a device, and the device we are searching via the help of system root. Why? Because it is the appropriate single point of contact between our Windows directory and the physical system. So this gives the control to the object manager, the main object manager in the kernel, which has the namespace and all the objects. Now this object manager will use its all features to find the full path to our requested device. And once the object manager has found the whole path, it will give away all of its control to the input output manager. And then after this, there will be whole set of different protocols that will be followed to return us the device which the user is searching for. So it's first the object manager and then it is the input output manager. And therefore, when we use this, we can actually extract the full path of our device. It will be shown in the other PDF which I have pasted screenshots of all these practicals. We'll move to it later on. Now the process and thread manager. Basically, when I told you that every task that is being performed is performed in form of a process on the operating system, and this process can have multiple threads. Now, for example, a user mode code is there, a file which is to be executed. It has a process created, and this process can have multiple threads. For example, let's say X. X can be any number ranging from 1 to any. Now, the problem is the in first case here, the user created its own codes process and it has this much threads. But what if there is an unknown process going on in the system which is having kernel mode, which is going on in kernel mode? Now, if the user is able to access this unknown process and is able to modify the security description of this process, like making himself the owner of this process, then he can simply misuse the privileges of this process to do malicious tasks. Therefore, a direct access by name to a process is not enabled in our system. Therefore, we can access interact with the process only via its ID. And this process ID is abbreviated as PID. So that was we are saying that user cannot access the process name, but it can interact through process ID, PID. Now, there are various kinds of process, but two main which we would like to tell here are the first one is idle process, which means that if the operating system is doing nothing, then an idle process is being performed and it has a PID of 0 in our case from the screenshot you will see later. And the system process is the one which is owned by the kernel and is used by the kernel to perform any kind of background privileged task using thread. It has the PID of 4 in our case. So like this demonstrates that we cannot literally see the names of the process, we can only have their ID. Now let's move forward to the memory manager. Now, as the name says, the main work of this will be to manage the memory that we are using. Now, basically, when we talk about our main process, this process has a kind of dedicated space, and this space consists of the virtual memory address. Like the actual address of this process is stored in a space, and it's called virtual memory address. Now, in case the process is a 32-bit process, then depending on the system, if the system is 32-bit, then the process can access up to 2 GB of data. And if the system is 64-byte, then the 32-bit process can access maximum of 4 GB data. However, if the process is of 64-bit, then it can access up to 128 terabytes of data. Now the chronology we will see here. Basically, the kernel has this subsystem memory manager that we are talking about, and this basically allocates the space for virtual memory address of the process. Now, this virtual memory address space that we are talking about, it is basically a kind of shared space, not unique and isolated for every process, but a shared space. Why? Because it is created by memory allocation. But don't worry, even though it is shared, the memory allocation has its own defined protection states, so that it defines which space has which permissions to a user, like read, write, execute, etc. And in this shared space, it consists of two important details. First one is the running state of the process, like what the process is doing, active, etc. And second one is the executable code, like what is the actual task that the process is doing in the system. Now, the memory region of this process has these four things. First one is the address of the process in form of hexadecimal, etc. on the hardware. Second, of course, the virtual memory. Second one is the size. Third one is the protection, like read, write, execute, etc. And last one is its state information. Now, this state is having three types here. The first one is commit, which means that the space being used here is allocated and is ready to use by the user, available. Second one is reserve. Reserve means that the space is allocated but not available to use yet. And third one is free, like it is neither allocated nor available to use, of course. Now, when we talk about this virtual memory allocation, it has a specific property which says that it has a minimum default allocation size as per the system. Like when we will see later the example in the other PDF, we will see that when we try to allocate a space of 1000 bytes, we were forcefully given a 4096 bytes space. Why? Because the minimum default size was 4096 bytes. Therefore, we cannot give a minimum or less space than the default set. Now, let's talk about the section object. Basically, there is another method to for the virtual memory allocation, which is the section objects. Now, section objects are also a kind of kernel objects which have a memory mapping feature. Basically, what the memory mapping means here is using the section object, we can directly read and write from the kernel object into our main memory, or we can share the memory between processes. Like for example, if we have two processes sharing the memory, then modifying one process will directly reflect the changes on the other. Now let's see the chronology of how all this works. Now basically the process, now when we create a section object for the process, first of all we have to specify what is its size, its protection, and an optional handle to the kernel object. Now then we have to map this section object into our virtual memory. And while mapping, we have to make sure that the original process and the section object must have the same protection type. Like for example, if the original one had read protection and the section object has a write protection, then because of them not being same, it will cause a crash and be not allowed. They should have the same type of protection. And then after mapping this section object, we have to supply it to the object manager namespace path, the main namespace directory which has all the objects of the kernel. And then basically we can create a shared process which has the memory. Now let's move to the code integrity. Now code integrity, as it says, that basically the kind of code or file that is being running on the system, we have to make sure that it is verified by the system and it is safe to run, like it is have from an authenticated origin. Now most of the time this code integrity is enforced in the kernel execution, because of course we have high level of privileges in the kernel mode, and optionally rarely when they find something suspicious in the user mode. Now everything that is can be executable on our Windows, it's signed and verified. Basically, we use a mechanism called authentic code in Windows, which embeds a cryptographic sign into each executable file. And this ensures that the we can analyze that if the process being executed, it's signed and verified by the Microsoft. Now here we got to mention that even though the once signed process, the sign will always remain, but due to the embedded information, we can check that whether the sign is valid or expired. The sign can still be there, but validity may not. Now let's talk about the advanced local procedure call. Now, as we talked earlier, it basically is used for the local and cross-platform communication between the different APIs of the Windows system. What we do here basically is we create a server of this procedure call. We put it into the object manager namespace from where all the objects can be managed, and basically the client object searches for our server into the namespace, and from there it can access the server. Now the last topic, the configuration manager. Now the configuration manager, which is also called a registry in Windows, it basically has all the configuration info of the overall system. Basically, it stores all the configuration information for each and everything in the system in form of key value pair, in form of folder and files. And this can be accessed only through the OMNS, the namespace. Now this is where our handwritten notes end. Here, the all the notes that I have used and written here are basically a kind of summary, a kind of mind map, a kind of logical connection that you can use for a fast understanding of all this concept. And the second PDF, this is where I have all the concepts having more elaborately explained along with the screenshots, which are the proofs of like how we can use special commands in PowerShell to see the working of all these types of concepts. I would request all of you to once go through this PDF, and wherever you see all this command, although the main like the handle duplication etc. I had explained, and you all know the basic types of system calls prefixes that I explained. It will be easy for you all to understand all this. It is basically the enumeration kind of commands of PowerShell. I would request that all of you once go through this PDF, once read them. There are 48 pages, and the second one was 22 pages. From this PDF, you will get a good idea of what all these things are in brief after listening to what I have explained all this time. And from the second PDF, you can instantly connect all the dots, like the logic between all these things, how they work in our system. So this was the second chapter from our book, Windows Kernel. There are up to 15 chapters in this book. So for each chapter, I will be having videos in which same way I will be explaining them through two types of notes of mine. First one is this PDF in which we will be having the elaborate explanation and also the screenshots of commands in PowerShell of how we can access, interact, and manipulate them. And second one will be my handwritten notes, which will be a logic connection mind map type. I will be uploading all these documents to my GitHub and give its link in the description. If you all think there was any kind of feedback you all guys wanna give to me, please drop them in the comments. Of course, this was my first video, so I was not that good maybe while explaining, but I'm sure I will be better at it by the consistency of various other teaching that we will be discussing together of the Windows internals. Thank you.